Hello friends, so we'll continue the second part of the basic thermometers which are used for temperature measurement. So far we have covered gas thermometers and we have covered liquid in glass thermometers. So in gas thermometers, if you remember, the main sensing parameters was pressure of the gas which was placed in the gas chamber. And in liquid in glass thermometers, the main sensing parameter was level of the sensing liquid, mercury or red alcohol or any other sensing liquid which is used. Next we have the electrical resistance thermometer and the thermoelectric thermometer. So as you can see, this electrical resistance thermometer, from the name itself you can get some indication of what is the main sensing parameter here. As you can see, resistance, okay, electrical resistance R, that is the main sensing parameter here. So how it is used to measure temperature, we'll see. So the electrical resistance thermometer, it is a type of temperature sensor and it is also called as RTD, which is resistance temperature detector. So we have discussed it in detail in sensors and transducers. If you want, you can watch it. So the basic concepts, its modifications, variations, other temperature measurement sensors we have discussed. So from the thermodynamics point of view, I am discussing all this. Okay, so it is also called as resistance temperature detector. So here we select certain metals which have certain properties in which the resistance of the metal, it varies with change in temperature, and this property is utilized as the main sensing property in electrical resistance thermometer. Okay, so it is a passive transducer because it requires external supply voltage. Active and passive transducer, if you remember, active transducers do not require a separate voltage supply, they generate their own voltage. Passive transducers require an external excitation voltage, supply voltage. So the commonly used metals for this temperature sensor fabrication or this thermometer fabrication, they are platinum, nickel, iron, tungsten, aluminum, copper, like this. Okay, but most commonly you will find platinum based electrical resistance thermometers or platinum based resistance temperature detectors. There are a lot of reasons for the selection of platinum. I have discussed it in detail in sensors and transducers. Here I don't want to go into detail about that. Here straight I want to go into the main working formula because we'll be using that for solving a lot of numerical problems. So the electrical resistance thermometer, it looks something like this. It comes in many designs, but these are the two simplest designs which you will have, where we have in the first design the substrate, a cubical kind of a structure in which the metallic wires, whatever metals are selected, platinum, aluminum, iron, tungsten, nickel, alloy, whatever it is, so it is inserted into that thing, and there are a lot of other internal circuitry present in that which gives us a proper output in terms of change in resistance. So this is the substrate type and this is the bobbin type, where we have a cylindrical base into which the metallic wires are inserted. Okay, these are the two design, simple design of resistance temperature detectors. So what is the relationship between temperature and resistance? So here the relationship between the resistance of the electrical resistance thermometer RT and temperature T is given by this. This is very important. There are two mathematical relationships. First one is something like this. the resistance of that particular thermometer at temperature T is equal to R0 into 1 plus alpha T minus T0. So here R0 and T0, they are resistance at the reference temperature, which is normally taken as 0 degree Celsius, and T0 is simply 0 degree Celsius, the reference temperature. Okay, it is called as reference temperature. Okay, R0 is the resistance at 0 degree Celsius and T0 is 0 degree Celsius. So it is used as reference. So first of all, for designing the thermometer, for calibrating it, it is taken and brought in contact with a container which contains ice, which is at 0 degree Celsius, and we take the resistance reading. So that is used as reference. Alpha is the temperature coefficient of resistance. Okay, alpha is the temperature coefficient of resistance, which is unique for each metal. For each metal it is unique and it is mentioned in the specification sheet. When you purchase a particular sensor, electrical resistance thermometer, it will be there mentioned in the specification sheet. And as you can see, there is a slight variation in the relationship where we have this much. Up until this much it is the same, R0 into 1 plus alpha into T minus T0, the difference between the specific temperature and 0 degree Celsius. Up to this it is constant. Then we have a higher power relationship, which is beta into T minus T0, the difference between the two temperatures, the square of that. This is for wide temperature ranges. This is for narrow temperature ranges, where the difference between the measured temperature and the reference temperature, it is not too much, but in this case it is too much. Okay, in this case we have another temperature coefficient of resistance, beta. So alpha and beta, they are temperature coefficient of resistance, which is unique for each metal, and it is used, it is mentioned in the specification sheet. So here, to make it simple, to get the temperature reading, we'll use relationship like this, which is derived from the previous relationship. So here what is done, to get the particular temperature reading T, because we want the output not in resistance, we want the output in a particular scale, whether it is Kelvin, Celsius or Fahrenheit or Romer, whatever it is. We don't want a resistance output in ohms. We want an output in terms of particular temperature scale. So what is done for calibration, we have a upper fixed point and lower fixed point. The upper fixed point, which is generally, if we take the Celsius scale, it is 100 degrees Celsius, and the lower fixed point is 0 degrees Celsius. So this is the lower reference which is used generally. So what is done, it is the particular thermometer setup, it is also brought in contact with boiling water, and we also take the reading at that boiling point, the upper fixed point, that is 100 degree Celsius. So when we have both the readings, resistance at 0 degree Celsius or lower fixed point and resistance at 100 degrees Celsius upper fixed point, we can calibrate the thermometer to give us the particular temperature reading as per this relationship. RT minus R0 by R100 minus R0 into 100, where 100 is the difference in the upper fixed point temperature and lower fixed point temperature. For Celsius it is 100 minus 0, which is equal to 0, because the upper fixed point is 100 degrees Celsius and the lower fixed point is 0 degrees Celsius. Same thing can be done for other scales also, Kelvin, Fahrenheit, Romer. You will get the same result, because the interconversion formula we can use to convert one temperature into another. So this is the simple one, because Celsius is the simplest to do. So we get a standard relationship here. So always remember this formula. This is the general formula. This is for applied for a particular scale. So temperature, any particular temperature reading, T is equal to resistance at that temperature minus resistance at lower fixed point for that scale by resistance at upper fixed point for that scale minus resistance at lower fixed point into difference between upper fixed point temperature and lower fixed point temperature. This is the thing. Same format. We use the same format for constant volume gas thermometer, where in place of R we had P. Pt minus P0 by P100 minus P0 into 100. In case of liquid in glass thermometers, in place of P it was level of the liquid, Lt minus L0 by L100 minus L0 into 100. Here the sensing parameter is resistance, so that's why RT minus R0 by R100 minus R0 into 100. So it all depends on what is the sensing parameter here. In case of constant volume gas thermometer, it was pressure of the gas. In case of liquid in glass thermometer, it was level of the sensing liquid. In this case, it is resistance of the metal. Okay, so this is the thing. So this is the basic operating principle of electrical resistance thermometer. So the next thermometer which we will discuss is the thermoelectric thermometer. Okay, so here the main sensing parameter is the EMF or voltage which is developed in the main sensing material as a result of temperature fluctuations. Okay, so here the main sensing parameter is EMF or voltage. So let's see how this whole thing is designed and what is its operating principle. So the thermoelectric thermometer, it is also called as thermocouple. We have discussed it in detail in sensors and transducers. If you want, you can watch it. Okay, so it is it operates on the principle of Seebeck effect. So the main design for the construction of this thermometer, it consists of two dissimilar metallic wires, okay, and they are joined together at 2 points. Okay, this is one point, and here also it goes and it is joined at 2 different points. Okay, like this. Okay, so these 2 points where the metallic wires are joined, they are called as junctions. Okay, junction. This is one junction, this is another junction where it is joined, and this is the body of the thermocouple where it has some internal circuitry which we will discuss later. Now so these 2 junctions which are formed, they are called as hot junction and cold junction. Why hot junction and cold junction? Because the hot junction, it is always placed in contact with the object or the surroundings where the temperature is to be measured. Okay, it is also called as measurement junction. The cold junction is kept in a constant temperature. Normally it is kept at a reference temperature in an ice container or ice bath which is at 0 degrees Celsius. Similar to what we did in electrical resistance thermometer, RTD. There also the reference temperature was at 0 degrees Celsius. So this is the reference junction or cold junction, and this is the measurement junction or hot junction. So here the thing is that when a particular junction is brought in contact with a certain temperature, it develops a certain EMF or voltage. As you can see here, it is represented by VH, the voltage or EMF at the hot junction or measurement junction, and this VC is the voltage or EMF which is developed at the cold junction or reference junction. And the difference between these two EMFs is measured with the help of a voltmeter, and this difference in voltage is what we get. Okay, because 0 degree Celsius is the reference, the temperature difference corresponds to the voltage difference. So it's something like this. So let's say the temperature difference between the two junctions, it is small t, where small t is hot junction minus cold junction, or we can write it as measurement junction temperature minus reference junction temperature, the difference of temperature between the two junctions. Okay, small t is the difference of temperature between two junctions. Now the reference junction or the cold junction, it is at 0 degree Celsius. Okay, so the relationship between the difference of EMF which is generated, the voltage VH minus VC between the two junctions, and the temperature difference between the two junctions, it is given by this. Okay, this is the potential difference between the two junctions. It is given by AT plus BT square plus CT cube. Always remember, this is small t. Small t is the difference of temperature between the two junctions. Okay, this is the difference of temperature between the two junctions. And A, B and C are respective constants for a particular material. Now, different combinations of metallic wires are used, copper constant and chromyl alumyl, platinum rhodium, chromyl constant. These are popular choices, because of their simplicity in designing them and the, how easily we can reproduce the output. There are a lot of complicated things which are there, which is not required here. From the thermodynamics discussion point of view, it is not required. When sensors and transducers, I have discussed it in detail. So these are the combinations. So for each combination, okay, copper constant, this is 1, copper is 1, constant is 1, chromyl alumyl, chromyl is 1, alumyl is 1. So each particular combination, for each particular combination, this A, B, C constants, they are different. Okay, and it is mentioned in the specification sheet. Okay, so the Seebeck coefficient or sensitivity is simply the potential difference which is developed divided by the temperature difference. Potential difference by temperature difference, this gives us A plus BT plus CT cube. It is called as the Seebeck coefficient or sensitivity of the thermocouple or thermoelectric thermometer. Okay, so this is the relationship between temperature difference and the potential difference between the two junctions. Now, how can we use it to calibrate the thermoelectric thermometer? So here again the concept is the same. We take the thermocouple, we bring it in contact with the lower fixed point for a particular scale. For Celsius, it is 0 degree Celsius. It is already there in the cold junction, the ice bath, and we take the temperature reading at 0 degree Celsius. Then we bring in contact the thermocouple with boiling water and we take the reading and we get 100 degrees Celsius, the EMF, the potential which is developed at 100 degrees Celsius. Once we get these two values, we can use it to get us an output in terms of degrees Celsius, because we don't want a voltage output. Whenever we use a thermocouple, we don't want a voltage output. Most of these setups, they are in digital format where we'll get a digital output on a LCD display. So we don't want a voltage output, because when we measure a particular temperature, we want to know how much Fahrenheit, how much Celsius, how much Kelvin, or how much Romer. Romer is not that used, but Kelvin, Celsius, Fahrenheit, how much it is that. So we don't want a voltage output. So we want to convert that voltage output, that EMF output, into a particular scale, temperature scale, whether it is Celsius or Kelvin or Fahrenheit, whatever. Similarly, in the previous setups which we used in gas thermometers, where the main sensing parameter was pressure, we wanted to convert that pressure into a particular temperature scale. Similarly, in liquid thermometer, the liquid level was converted into a particular temperature scale. Okay. Similarly, in resistance thermometer, we converted the resistance into a particular temperature output. Here we are doing the same for EMF or potential difference. So here the temperature is given by, the specific temperature reading is given by the voltage or the potential difference, the EMF at that particular temperature minus the EMF at 0 degree Celsius or lower fixed point, divided by the EMF at 100 degree Celsius or the upper fixed point, minus the EMF at 0 degree Celsius, the lower fixed point, multiplied with the temperature difference between the upper fixed point and lower fixed point. In case of Celsius, it is 100 because it is upper fixed point is 100, lower fixed point is 0, so it is 100 minus 0, 100. Okay, so this is the main relationship which is used to calibrate the thermometers. The same thing can be done for other temperature scales also. Okay, Kelvin, Fahrenheit, Romer, you can do the same thing, where we have to substitute only the the lower fixed point and the upper fixed point, that difference, and everything else accordingly we will substitute. Okay, so this is the general format. Always remember this general format, this formula. Okay, and here this this thing, it is the main sensing parameter. When it is thermoelectric thermometer, it is EMF. When it is resistance thermometer, it is resistance. When it is liquid thermometer, it is liquid level. When it is gas thermometer, constant volume gas thermometer, it is pressure. So format is the same, just what is the main sensing parameter, what is the upper fixed point, lower fixed point, what is the particular temperature scale which you are using. That things you want to know, and then you can substitute the values and get the result. Okay, so this is the basic operating principle of thermoelectric thermometer or thermocouple. Okay, so here we have discussed the 4 basic thermometers, and on the basis of this we'll be solving some numericals. That's why I thought I should discuss this. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.